Welcome, everybody, to Modernizing Your Application with Containers and Serverless. First, thanks for coming to both Ignite and sticking it out to the second day. I know the last couple sessions can kind of be taxing on our brains. It's pretty exhausting to consume this much information. I want to get a quick survey here. If I can see everybody through these crazy lights up here, I'm getting a tan. How many people here are using containers in production? And I don't know, 20, 30 people maybe? Okay, how many people here are vaguely familiar with containers and what they are, what Docker files are? Okay, so a fair amount of you. So my name's Erik St. I am a developer advocate at Microsoft, where I get to focus primarily on open source technologies, especially around containers and container orchestration. So today we're going to talk a little bit about the container offerings that we have at Microsoft to be able to run container workloads on Azure, and why you might want to choose one over another. And towards the end, we'll have a short little demo of using serverless so that we can migrate into the cloud. All of the code and demos are available at this link. I'll put a slide up at the end with those on there for you again. All right, our mission. Anybody heard of this Tailwind Traders acquisition? This is probably the first talk you've seen that, right? So we're going to continue along with this kind of storyline that we've been acquired, we want to migrate to the cloud, we want to stop focusing on our own infrastructure. But where do we start? Especially around containers. We're kind of sold on containers. They feel like the right thing to do. And we'll talk a little bit about why they're the right thing to do. But there's a lot of offerings, and kind of choosing which option is appropriate can be difficult sometimes. So first, it'll help to take a look at what our current architecture is. So we're starting with our current platform, which is running across 3 virtual machines. We have a couple of microservices talking to some back-end databases, and finally a front end written in React. And these are all running on their own virtual machines. And we don't want to think about virtual machines anymore. We want to use containers. So containers, what are they? Why do they even matter? What's wrong with virtual machines? So if we think about a traditional application deployment, it might look something like this. We have a virtual machine. We've provisioned it with all of our dependencies that we need to run various applications. And they probably depend on a couple of shared libraries, hopefully the same shared library. Otherwise, we end up with this condition. And this has never happened to anybody before, right? We end up with 2 applications, and they both need different versions of some dependency. Well, how do we handle that? And this becomes a really difficult problem to solve, and additionally, it creates cruft. Maybe eventually we migrate application 1 to use version 2 of this dependency. But do we really want to remove that dependency? What happens if we need to roll back? What happens if another application comes out that needs that first dependency? And our machines just build cruft over time. So the first problem that containers solve is a packaging and deployment problem. So we can take our application, we can bundle it with all of its dependencies, and we can move it around with those dependencies, which solves 2 problems. We don't have the kind of dependency hell problem where 2 applications need different versions of a dependency. We also solve the cruft problem when we sunset this application, which in some cases we never do. We can remove all of the unwanted dependencies with it, and we also solve the problem of the works on my machine problem. We can guarantee that all of the dependencies are the same. The second problem that it solves is a distribution problem. How do we get our applications onto these machines? So when we take our image that's packaged up with our dependencies, we can push it out to a container registry, and it's able to be pulled from that registry. The orchestrators or whatever you're using to run your container only need to know how to authenticate with the registry. They don't need to know anything else about your application. They don't need to know about all of the configurations that need to take place or dependencies that need to be installed onto the host node. So they create clear boundaries for your applications, so we know which dependencies belong to which applications. We get to remove cruft from our virtual machines that eventually builds up over time. We get better resource isolation. without the overhead of having virtual machines. And we also get better resource utilization. And I'm trying to remember where I heard this statistic, but I think it's about 30% is the typical CPU usage for a virtual machine. And we can get up closer to 70, 80, 90% by using things like container orchestrators. So we can pack our applications much more densely. And we also get repeatable builds, and we'll talk a little bit about how we can use containers to do the builds so we don't have these magical build environments that have this pristine configuration that if anybody changes, the builds start breaking. So how do containers work? Is anybody here familiar with how a container is actually implemented? Okay, so we got a couple people. Does anybody want to come up here and do it? No? Guess it's me then. So containers, I know that especially in the beginning when containers first came out, you would hear expressions like this. It's like a lightweight VM. But this is actually inaccurate. A container is actually more like a highly configured process. So in the Linux world, we should ask this question. Linux people? All right, I'm in trouble. So all of you, this is accurate for you. All of the rest of the Windows people, you can all call me a liar, because in Windows, containers are virtual machines. They are kind of slimmed down Hyper-V, and we can talk a little bit about how that works in the future of that. But from Linux, where the container thing and Docker began, they're actually based off of kernel features that have been in the Linux kernel for more than a decade. It's based off of two kernel constructs. One is called C groups. So C groups control what resources that an application can consume, how much CPU, how much memory, how much network, and namespaces. And namespaces are what can this application see. And not just directory structures and things like this. Can it see other processes on the system? What network interfaces is it able to see? And this is what's always created the illusion that you're in a virtual machine when you exec into a container, is because your process gets put in the same namespaces as that application, and you see what it sees, which is only itself. So the image format we can think about is just basically a zipped file that bundles up all of the dependencies, which is your root directory. It's basically everything that would be on the hard drive, and that gets zipped up, and it's in a copy-on-write file system. But when we think about the basics of a container and how it works, the container runtime is pulling down an image, which is a zip file with some metadata in that. It extracts it into a directory. It executes the application, and then walls it off, makes it so that it can only see what's in that directory, makes it so it can only see its own process, it can only see its own network interface. Is everybody with me so far? Okay. And Windows people, again, I'm a liar because they really are virtual machines. So containers don't virtualize the underlying hardware, except for Windows, which is most of you, so again, I'm a liar. So they offer a degree of isolation, but they're not a hard security boundary. So in the Linux world, if you're running just straight Docker, and I find a kernel level vulnerability, I can use that to escape the container. Now, there are controls that we can put in place, AppArmor, SE Linux, changing seccomp profiles, not running containers as root, disabling privilege escalation. There's a lot of things that we can do to harden this and make it nearly impossible, if not impossible, to escape the container. But it takes understanding those types of security controls and putting them in place to do that. On the Linux side, there are options for doing virtualized containers, things like Kata containers, which uses KVM to run your application inside of a container. And we'll talk about Microsoft and Azure's container offerings, and those are virtualized. So even though you're running a container, a Linux container, it's running in its own virtual machine, so you do have that hard virtualization security boundary. All right, Docker files. Anybody familiar with Docker files? A couple people. So we're going to take a look at a Docker file and hopefully walk through what one looks like. So in our source directory, we have a couple of services, our front-end inventory and product services. And we'll just pick one at random and take a look at the Docker file. So what this is the from is the base image, and we can think about that as the zip file as it exists already. And we're going to pull that down, and then we're going to add stuff to that directory. to that folder. So we're exposing ports. So we're saying that we're going to, this is just setting an environment variable first to tell the application what port we're running on. Then we're going to expose this port. This is letting Docker know that we need to open up port 8000 to clients. And then we're going to execute these things inside the container. So we're going to make a directory /app. We're going to set that to our working directory. And then we're going to copy files from our local environment. So when we build this, there's something called a build context, which is all of the stuff that we're copying into the Docker build context. And this is us copying that source code into that path. We're going to run npm install, which is going to produce more artifacts spread out across that directory structure. And here we're basically copying everything from our current working directory into the working directory that we set this /app inside the container. And then command is what the container runtime is going to execute. This is the application that's going to run. And with just using this, Docker is able to produce the directory structure that gets bundled up into the zip file. And it's also able to be aware of what needs to happen when it's executing. So another fun fact about the way this works is each one of these lines produces a layer in a copy on write file system. So we're able to cache all of these things. So if I come down here and I just add one more file, I'm just copying in one more file or setting one more environment variable, none of the previous steps have to be ran again when I do a Docker build. And it also doesn't have to be pushed or pulled to or from the registry, only the changes. So it's important to think about this for two reasons. One is if some part of your Docker file is going to change regularly, the further down in the Docker file that you can change it, the less work that has to be done, the less stuff that has to be transferred to and from the registry. The second important fact to remember about this is when I said this creates a layer in the image, is that if you're creating artifacts that are going to be removed, say they're build time dependencies. So you install a bunch of stuff to do the build of your application, and then you delete it using another line in the Docker file. That is not going to produce a smaller image size. And that's because that layer is saved, and those layers are the things that get transferred to and from the registry. So if you add that all to one line, the result of that entire line is what gets committed as a layer. Everybody with me? I know it's late. Okay. So what else are Docker files good for? So we can also do these things called multi-stage builds. And this is an example of that. We can look at the from that we just saw, and we're using an Alpine Linux distro as the builder, and then we're running a couple of commands, including the Go build. Do we have any Go programmers here? I can't see a single hand. Nobody? It's just me? All right, so we're gonna build our Go application, and what happens is this is all in one image. But down here, we see the start of a second image. So Scratch is a Linux container that basically has nothing in it. It's not a Linux distro. And we use this if we only have a self-contained binary that has no dependencies. So we're creating this second image. And in here, we're copying over artifacts that were produced in the first image. So this allows us to do the build inside of one container and be able to have that completely reproducible so we don't have to have some pristine build machine. It's able to produce the artifacts, and we don't have to worry about all the build time dependencies being inside of our runtime container. So this makes smaller images. This also makes things more secure because there's a less attack surface in the runtime container. Okay, so we have our container. How do we get it into the cloud? So Azure has a couple of options for this, the first of which is Azure Container Instances, which we can think about as containers on demand. It's actually a container group, so you can execute one or more containers side by side, similar to the concept of a pod in Kubernetes, if you're familiar with that. and your build per second that this lives. And there's lots of integrations with Azure services, and you don't need to provision any Kubernetes clusters or virtual machines, even though your container is running in a virtual machine. There's flags for being able to say whether or not you want this exposed to the public, so you can get a public IP address. We can mount persistent storage in, and we get support for both Windows and Linux containers. When is this useful? Mostly for short-lived processes, maybe batch work. If you're doing machine learning models, you can span this out really, really wide and pay only while it's running. CI/CD workloads would be good for this. The reason I say this is currently the pricing model on it. If you have long-running services, it's going to be cheaper to use one of the other options. If you want to use this one, feel free. Microsoft is happy to take your money. It keeps me doing open source work, so creating it, command line people. All right, we've got I don't know, maybe 10, and there's I don't know 15, 1,800 people in this room. Okay, so I'm a command line person. We'll look at this in both the portal and here as well. We also have Azure Kubernetes Service, which is our managed Kubernetes offering. I'm not going to go into too much detail here. If you're interested in container orchestration and Kubernetes specifically, if you hang out here with me in this room, the very next talk, we'll spend an hour talking about Kubernetes and how it works. Another thing is Azure App Service, or web apps for containers. You may have heard it. And Azure App Service itself is a managed platform for running applications. So if you have things like Node, PHP, .NET, Python, we're able to just take that application and deploy it out. But we also support running containers this way. So if you have a website or an API service that's HTTP, this is a really, really great way to do it because we can bolt on things like single sign-on. We give you metrics for requests per second and latency and things of that nature just for free. And of course, it has lots of integrations with other Azure services. It can also do continuous delivery. So it can monitor Git or other source control systems for commits and then be able to pull in the changes. And it can also look at Azure Container Registry when you've pushed a new image. We do offer high availability and auto scaling so that you can get more instances of it as your application CPU utilization climbs. Okay, so Azure Container Registry. We can't get our containers into any of these things if we don't have anywhere to pull it. So I should say that all of our container offerings can pull from any registry, whether you're hosting it yourself using Docker Registry or Harbor or things like that, or you're using the public Docker thing. ACR, you get some advantages. So ACR, you can use the same Docker commands. You just Docker log in the same way you would to another registry. But we replicate these images. So if you're running in multiple regions, once you push to the registry, it's going to exist in both places, and you're going to eliminate kind of that cross-WAN traffic to pull images down from wherever your registry happens to be running. We also offer authentication with Active Directory. So if you're highly dependent on Active Directory, this is a great way to stay in there, and we can give people permissions on which containers they're allowed to pull, which containers they're allowed to push, things of that nature. We also do vulnerability scanning. So whenever you push an image to ACR, we're going to go ahead and scan it looking for known CVEs against things in that container. And a cool feature that came out recently in the past few months is container registry tasks and builders. So if you have one of those multi-stage Docker files, we can watch your Git or source control system for a commit, and we can pull all of the code and run that builder in there, generate the image, and then store it in ACR for you. And you don't have to have any of that stuff running, any CI/CD stuff to do that inside your own infrastructure. All right, so we've looked at kind of our container offerings and what's available. So I think for this particular case, obviously we have to use Docker. There's lots of stuff on Hacker News about it, so we know we need containers. We'll use Azure Container Registry so that we can keep our images inside of our network and we don't have to worry about all that ingress and egress traffic. And we're going to use Azure App Service as our container orchestrator because we just have a couple of services There's not a ton of service discovery needs and things like that. If you hang out for the next talk, we'll talk a lot about the container orchestration and what you get. But in this particular case, it's probably going to be a lot more cognitive overhead to take on something like Kubernetes for this use case. I've got a couple of make commands here, and this is just so that nobody has to watch me fumble typing and we waste a bunch of time. So this is just going to run a couple of commands, and we'll stop and we'll talk about each of those commands. So in this case, we're doing a build in ACR. So we're just using the AZ tool, telling ACR to do a build. We're telling it which registry we want to push things to, what the image is going to be. And this is a couple environment variables that are used during the build. And we'll let this build. And this is just going to wait for an agent. And now it's picked it up, and we're getting all of the logs from Docker build running inside of ACR. And in these particular cases, we can see a lot of these verifying checksum and download completes. Nothing's really changed. I haven't modified the code since the last time ACR did the build, so it doesn't really have to do any real work. It's just using those cached layers. Now, if you trust me that these are already in there and it's the same thing and I haven't modified anything, we can also look at what we would do if we just wanted to use Docker. So the first thing we'd need to do if we go into the portal and look for our container registry, under access keys, please nobody hack my stuff, we can get our login server, and we can do a Docker login and pass. And I'm already logged in. So, but this would prompt us for a username and password, and we can grab those from here. And we would just Docker login, and then we can do, let's cd into source front end. So we can do a Docker build. We need our, we're going to tag it. So this is our login. So all images are going to be prefixed by their registry URLs. So in this case, we're going to call it front end, and we're just going to call it 1.0.0. And we give a dot for our build context, and it's already been built, so we can see here using cache. So nobody has to wait for this to build. And then we would just do a Docker push, and I copied that. There we go. So we have our images in the registry, and we know we want to use Azure App Service and web apps for containers to run these containers. So command line is a simple AZ web app create. We need to pass it what resource group to go in. We need to pass it the number of instances or the name, and a plan. The plan is which SKU we want these containers to run on, how much CPU, how much memory, whether it's Windows or Linux. And then we pass it the image. So we're going to go ahead and deploy these out. And again, these are just scripts so that you don't have to watch me type and miss flags and have to go fix my deployment and all of that good stuff. So the first thing we're doing is we're creating a plan. We're just giving it our resource group and the name of our plan. We're telling it it's going to be Linux, and we're going to use a P1v2. And I'm going to walk through this in the portal as well. Back in on this. OK, so this one is creating the front-end service. So we're giving it the resource group, a name. We're telling it the plan that we just created. And then we're giving it the container image that we want to run. So in the portal, similar thing. We're just going to give our app a name. We're going to pick a subscription. There we go. We're going to tell it which operating system, and then we can choose either an app service plan that exists already, or we can create a new one. Then the interesting thing here is how do we get the container? So we've got a number of ways that we can do this. We can pull it straight from Docker registry and things like that. We can use Azure Container Registry. So if I pick my container registry here, let's check in on this. Okay, and then we can pick our front-end image, we can pick the specific tag, and then we can change the startup file. And if you're running private registries, all of these are options. Okay. This is deploying our inventory service. And then we have one more. We have our product service that needs to be deployed. And then if everything works, hopefully, nothing ever goes wrong in conference demos, right? Okay, now we have our product service doing the same thing. And we could have done this through the portal or the command line for reproducibility so that I don't fail miserably in front of lots of people. I try to automate this as much as possible. And so once this is running, we're going to start tailing the logs, and Azure gives us a command that we can use for these to be able to attach ourselves to the container logs and start monitoring it. And we're going to do that just to see when the application starts up to give me the best chance at success. Is everybody rooting for me, or does anybody want me to fail? Does anybody want to see a just terrible demo at the end of the day? All right. Okay, so now we're going to use AZ Web App log to be able to tail our logs really quick and wait for our front-end service to come up so that we can hit it. I love conference Wi-Fi. Okay, so now we're connected to the log streaming service, and we're going to start pulling our logs. And any second now, it will tell me it started. Here we go. And here is our application running up in Web Apps for Containers. And it's going to take a second while it pulls in all of the products, but we should be able to see those render here in a second. Some of those services are probably still starting up. This will be the time that it fails. It works. All right. Now, I'm going to tell you there is a problem here. Our inventory count there is just spinning. Why is that? Well, let's talk a little bit about that. This is just a little sidebar about the fact that I'm using Makefiles and how they work. If you're not familiar with them, you just start a target. That's the thing I'm doing where I say deploy, and then you can have dependencies of other tasks that get ran. Okay, so our problem is that some of our containers need credentials to be able to communicate with the databases that provide that data. But how do we get those credentials into our container? So we could hard code the secrets into the Docker file, but that would be ridiculously insecure. And you really wouldn't want to build a new image every time your credentials changed either. We could hard code it into the provisioning scripts like I just had. That also would be insecure. We don't want to store secrets inside of our source control. So how do we securely get them into our containers? So one option would be use something like Azure KeyVault, which is a secret management store. It has things like even hardware security modules if you work in an environment where that's required. So you can store encryption keys, generic secrets that you have, as well as certificates. And then you can use things like Azure Active Directory to manage who has permissions to which secrets, whether they can read to them or write to them, or even specific things like you're only allowed to commit secrets to KeyVault, you're not allowed to commit certificates, things of that nature. Creating a KeyVault is pretty straightforward. It's a single command on the command line. We can also do it from the portal. Let's see. Portal. And create a resource. And it's pretty straightforward. We're going to give it a name, and we're going to, there we go, resource group, ignite. And then we have different pricing tiers. So these are based on whether or not you need a hardware security module and whether you need kind of geo availability of these things to run at different places. These are our different access policies for our users. And this is to configure what's allowed to communicate with it on what VNet so that you can kind of wall off your KeyVault. Oops. OK. So storing a secret's pretty straightforward. We give it our vault name, we give it a name, and we give it our value. And we can do the same thing inside of the portal. And if I go under, oops. Oops. Here's my vault. And under here we can see keys. And we can just create them. We can say what type it is, how we want it encrypted, all of that good stuff. And our secrets. And here's our database connections that I already have stored in here. And the fun thing about this is we can actually track all of the changes. So that if you need to go back, somebody overwrote a secret or a key or certificate, you're never going to lose that. OK. So reading a secret is also pretty straightforward. We just saw that in the demo. In the portal, there's a button where you can copy the secret if you want without ever showing the value. But pretty straightforward, single command line. The only confusing part about this probably is that -o TSV. That's just saying that I want it output in tab-separated value format. Another option that you have is reading secrets directly from the application. So rather than setting these values inside of our, let's take a look at that real quick first. So if we go to our apps that were created here, here's our front-end web service that we have deployed. And underneath our application settings, we're able to add custom environment variables that will be seen by our application when it runs. So this is basically where we would store those credentials that our application needs. And we can do this in an automated fashion during provisioning. It'll use the local administrator who's doing the deployments, credentials to go out to KeyVault, get the key, and then store it into one of these secure places inside the web app. But we can also make the application itself request the key. And we have a bunch of SDKs for various languages to be able to do that. So let's go ahead and see whether we can fix this. Oops. So the first thing we need to do is store our secrets. So the first one we need is our MongoDB connection, which is actually going to be hosted by Cosmos DB with a MongoDB driver. Everybody take pictures. I'm waiting to see all of the fun stuff that you put in my database for me. Oh. It was a good thing you couldn't see. I don't trust any of you. All right, I can scroll up here just so you can see kind of what the command looked like. It's the Azure KeyVault secret set, and we're giving it our vault name, and we're giving it the name WebDB2 connection, and then this is just a long connection string that's going to be used by our application. Okay, so now that that's there, we're going to redeploy all of our web apps to be able to read environment variables that have those connection strings that we just pulled from KeyVault. Let's see. This was our front end. No, this was our inventory service. And loading. OK. So now we're going to tail our logs and wait for the service to come up. And then hopefully, with any luck, our service is fixed. I'm getting a tan up here. OK. This might not have logs. Let's see. As long as our service comes up, we should see an inventory. There we go. We are working again. So we're going to go ahead and change some of our counts for some of our products, because we're going to use this later. And apparently, we deal with fish that don't look like fish at all. OK. Next. All right, so let's talk about serverless. So serverless, I actually feel, is an overloaded term. Most of us use the word serverless to basically interchangeably with functions as a service. And I think that functions as a service is an implementation of serverless. But I think serverless really is when we stop thinking about the virtual machines. We stop thinking about the nodes. So anything where you don't have to think about nodes is serverless. So we're going to do a quick demo on serverless. It's a cram-packed talk, so we don't have a lot of time to go into huge detail. But we want to solve one particular problem that we had. This is an inventory service, and we're tracking inventory. And of course, management wants nightly reports to be emailed about things. But on our virtual machines, those were in cron jobs. How do we run this now, right? Our applications are inside containers. They're running in the cloud somewhere, but how do we manage cron jobs? So one interesting way to be able to do that is to leverage functions. So Azure functions allow you to have small snippets of code. I suppose you could have big ones if you really wanted to, that are able to react to external triggers. Things like an email coming in, or say a file being dropped on FTP, things like that. And we can use these a lot to glue services together to create kind of this evented model where we don't have some application constantly polling to make sure to see like if there's a new commit on Git or something like that. You're able to just wake the application up whenever this takes place. So they're typically small applications with very simple deployments. But one timer that is of particular interest to us is the timer trigger, or one particular trigger, I should say, is the timer trigger. And this allows us to set an interval for our function to be called. And that sounds a lot like a cron job or a scheduled task. So let's take a look at using a function to solve this problem. All right, so we're going to go under reports. And so the code itself, JavaScript people here anywhere? There's a few. Is this everybody's .NET here, right? C#? Is that where all the hands going to go up? Okay. All All right, so this is pretty straightforward code. It's just going to go out to the database and get a list of all of the SKUs that the inventory amount has changed. And we're going to call this send email function, which is just going to use SendGrid to send an email to me telling me about all of this changed SKUs. And here's the function to get the SKUs. So that's pretty straightforward. That could be code written in a number of languages. The important part is the function. So this is how we define a function. We're going to set bindings. So first we need to tell it the type, name, obviously, of our function. Our trigger type is a timer. The direction is in because this is a trigger that we're reacting to. And we'll talk about the direction out here in a second. And then we can set a schedule. And if you're familiar with Linux cron job syntax, this is the same exact syntax. We're saying that every 24 hours, we would like to run this particular task. So down here, we have our second binding with a type of SendGrid and a couple of parameters that need to be passed in. And we can see the direction is out, because when our function completes, this is what we want to take place. OK. And while this is running, I should open my email. OK. So we just run a command locally, and you can do this through IDEs too. I know that Visual Studio Code has plugins for this, and I'm sure that Visual Studio proper also has plugins to be able to do just single button click, deploy your function. I happen to come from a Linux background, so I use a lot of command line, and I probably need to get better about that. So what this is doing is it's packaging up all of that code I just showed you, along with the metadata, and pushing it up to Azure to deploy. It's a long time for 4.6 megabytes. Who's watching YouTube videos? I'm not that boring. OK. Then once this is running, there's actually two functions. So we can take a look at here, this direction. I created a separate function here called run create report. And this just is an HTTP trigger, so that when I hit a particular URL, it's going to call the same function. And I did this because I didn't think anybody wanted to wait 24 hours with me for this to go. I like hanging out and answering questions. I don't know about 24 hours straight. OK, so we're just going to curl this URL really quick to kick off that trigger. And then if we are lucky, any second now, we will get our email with the list of SKUs that we changed. So now we've migrated completely from our virtual machines, and we no longer have any virtual machines. We have solved dependency problems and deployment problems and build problems, and we've made everything significantly easier. We don't have to manage virtual machines anymore. So if you want to learn more, I know that this is a pretty quick pass over this stuff. I typically do like multi-day workshops on containers, so there's only so much stuff that we can get in. First thing you can do is check out the docs for all of our Azure container offerings. There's a link up there for KeyVault and also functions. I will give everybody a second to take pictures of that. At the end, I will also put up my Twitter handle and email address, and please feel free to email me or DM me. My DMs are open if you have questions about other areas of containers, and I'm happy to answer them or point you in the right direction or find people smarter than me who can answer your questions. If you're interested in container orchestration and container orchestrators and Kubernetes in particular, if you hang out here, 3:30, I will be giving a talk where we will talk completely about Kubernetes. We'll talk about kind of the basics of it. We'll talk about how the control plane works and all of that good stuff. So if you want to take a picture of this slide, this is where you'll be able to find all of the slide decks for all of these links are for all of the sessions that you've seen throughout the entire conference, and as well as all of the example code. And with that, I will be hanging out up here until the next talk, so feel free to come up and ask me questions. I'd love to do it from here, but this is a big enough crowd where I'd probably struggle hearing all of you. So please feel free to come up and ask me any questions that you have around containers. Even if you have questions about Kubernetes early, feel free to come up and ask me about those. Thank you all so much.